Good morning, students. The next theorem is mean value theorem. Mean value theorem is also very important thing, important one. Rolls theorem, mean value theorem. Right. Next one is intermediate value theorem. Here, mean value theorem. What is the state and prove mean value theorem? Let f be a continuous function on closed interval a comma b, and f is differentiable on open interval a comma b, then there exists at least one x in open interval a comma b such that f dash of x is equal to f of b minus f of a by b minus a. This is the statement. A question about state and prove mean value theorem. So you have to write the statement. F is continuous on closed interval a comma b and is differentiable on open interval a comma b. Then there exists at least one value, say x between a and b, such that f dash of x is equal to f of b minus f of a by b minus a. That is a statement, right? Now see here what is the given data in our statement? F is continuous function on closed interval a comma b, right? And f is also differentiable on open interval a comma b. Now we constructed a graph, right? Now this is the point represents a comma f of a, and this point represents b comma f of b. So where x a is x coordinate and the f of a is y coordinate. Here b is x coordinate, f of b is y coordinate. When you substitute x is equal to a in the function, you will get y value. Right? Now that's why I'm writing f of a here and f of b here. X coordinate, y coordinate, x coordinate, y coordinate. Now the graph, if you plot the graph, it will look like this. Is a continuous differentiable function, no? Right. Now if you join these 2 points, you'll get a straight line. This dotted line is a straight line. Now see, let L be a function whose graph is a straight line connecting a comma f of a to b comma f of b. Now we have to construct a graph. We have to draw a line passing through those 2 points. What are the points here? A comma f of a and b comma f of b. Now that dotted line is a straight line, no? Right, which is passing through a comma f of a and b comma f of b, those 2 points. Now see here, L of a is equal to f of b and L of b is equal to f of b, clearly from the given thing. Now here L dash of x is equal to, if you know the straight line, we can find a differentiation of that straight line. That means if you differentiate that one, you will get the slope of the equation, right? Suppose if a line is passing through 2 points x1 y1 and x2 y2, what is the slope of this line? Is nothing but y2 minus y1 by x2 minus x1. This is the slope, no? Similarly, the line is passing through a comma f of a. This is the first point, b comma f of b. What is the slope of this line which is passing through these 2 points? Means y coordinate difference, f of b minus f of a by b minus a, no? Now this line is denoted by L of x. Now this is nothing but the slope of that line L of x is nothing but L dash of x. Now L dash of x is equal to f of b minus f of a by b minus a for all x, right? Just we are writing the slope, that's it. Now we are defining a function. Let g of x is equal to f of x minus L of x, right? Here f of x is continuous, L of x is also continuous function, therefore g of x is also continuous, right? Because f is already continuous function, L of x is a straight line which is also continuous function. If you subtract one continuous function minus another continuous function, you will get another continuous function, right? Here g of x is f of x minus L of x for x belongs to closed interval a comma b. Now we are defining this function. Now we are checking whether this is continuous or not. Yes, it is continuous. Sir, why sir? Because these two are continuous functions, right? Therefore obviously g of x is also continuous on closed interval a comma b. And what is f? Given that f is differentiable on open interval a comma b, and we know that L of x is also differentiable. Every straight line function is differentiable, every straight line graph is differentiable, therefore L of x is also differentiable. Therefore now we can say that g of x is continuous on closed interval a comma b and also differentiable on open interval a comma b, right? And find, you know, g of a, f of a, g of x is equal to f of a, no? See, Now g of x is equal to f of x minus L of x. Now if substitute x is equal to a here, g of a is equal to f of a minus L of a, right? Now this implies g of a is equal to f of a is nothing but L of a, no? L of a is nothing but f of a, therefore this becomes 0. If you substitute x is equal to b here, now g of b is equal to f of b minus L of b, right? Both are same, therefore this is also 0. Now we know that g of a is 0, g of b is 0, because we are using this function, right? In the place of x we are substituting a, in the place of x we are substituting b, and we got g of a is equal to 0, g of b is also 0. Now so that means the function value is always equal to 0 for all x belongs to the open interval a comma b and close interval a comma b, no? Therefore g dash of x is obviously 0, because the function g of x is 0 for all x, right? That means g dash of x is equal to 0, no? Right? See, therefore g dash of x is equal to 0 for some x belongs to open interval a comma b. Why? Because the function itself is 0, right? G of a 0, g of b 0. At the extreme end point the values are 0. That means the differentiation of g of x is 0 for some x belongs to close interval a comma b. Now by Rolle's theorem we have, see, now we know that g dash of x is equal to 0, no? What is g of x? This one. If you differentiate this one, g of x is equal to f of x minus L of x, no? If you differentiate this one, g dash of x is equal to what you will get? F dash of x minus L dash of x. We know that g dash of x is equal to 0. Therefore, f dash of x minus L dash of x is equal to 0. This implies f dash of x is equal to L dash of x. Now what is L dash of x? L dash of x is equal to f of b minus f of a b minus c. Now just now we wrote, no, L dash of x is equal to f of b minus f of a by b minus c. Now L dash of x is nothing but f dash of x. Therefore f dash of x is equal to f of b minus f of a by b minus c. That's it. See, this is Cauchy's mean value theorem. Now see, here g dash of x is equal to 0 for some x belongs to open. By Rolle's value theorem, that means f dash x minus L dash of x is equal to 0. F dash of x is equal to L dash of x you are getting. What is L dash of x? Here f of b minus f of a by b minus c. Therefore, f dash of x is equal to f of b minus f of a by b minus a for some x belongs to open interval a comma b. This is called mean value theorem. Next one is next theorem. Let f be a differentiable function on open interval a comma b such that f dash of x is equal to 0 for all x belongs to open interval a comma b. Then f is a constant function, right? See here, some example I am giving you. Say f of x is equal to 2 for all x belongs to 3 comma 6. Now what is f of 3 value? 2 only. F of 6 value? 2 only. Now f of 4, 2 only. Now x you can take 3, x you can take 6, x you can take 4, x is equal to 5 and so on. No? The numbers lies in between 3 and 6. For each and every value of x in closed interval 3 comma 6, the function value is always equal to 2 because it is a constant function, no? Right? Now that means f of x is equal to 2 for all x belongs to the closed interval 3 comma 6. Now what about its differentiation? If you differentiate this function, the differentiation of f of x is 0 because it is a constant function. Similarly, see here. Now once again, please read the statement. Let f be a differentiable function on open interval a comma b such that f dash of x is equal to 0 for all x belongs to open interval a comma b. Then f is a constant function, right? F is a differentiable function on open interval a comma b, and given that f dash of x is equal to 0 for all x belongs to open interval a comma b. That is the given data. Now we have to show that f is a constant function. right? Let us suppose that f is not a constant function. We are proving this theorem by contradiction way. Now, if f is not a constant function on open interval ab, then there exist at least two values, say x1 and x2, such that a less than x1 less than x2 less than b, and f of x1 is not equal to f of x2. We are assuming that f of x is not a constant function. Not a constant function means it must be like this. See, f of x is equal to x square. Suppose for all x belongs to 2 comma 4. That means there exist at least two values, no? 2.5 and 3, which are lies between 2 and 4, no? Right? These are nothing but a and b. This is x1, this is x2. F of x1 is equal to f of 2.1 is equal to 2.5, whole square. That is 6.25. F of x2 is equal to f of 3 is equal to 3 whole square means 9. Right? Like this. Now, see here whether f of x1 is equal to f of x2. 6.25 is equal to 9. No. F of x1 is not equal to f of x2. Now, by mean value theorem, for some x belongs to this open interval, we have f dash of x is equal to f of x2 minus f of x1 by x2 minus x1. No? What is mean value theorem? If f of x is continuous and differentiable on open interval, closed interval a comma b and open interval a comma b, then f dash of x is equal to what you will get? F of b minus f of a by b minus a. No? Similarly, if f of x is continuous, this function is continuous on the interval x1 x2 if you choose, then by Cauchy's mean value theorem, this f dash of x is equal to what you have to write? F of x2 minus f of x1 by x2 minus x1 you have to write, and which is not equal to 0. Reason is what? Since f of x1 is not equal to 0, f of x2 is also not equal to 0, and x1 is not equal to x2. See, x1 is 2.5, x2 is 3. Obviously, this is not equal to 0. That means which is a contradiction. Why it is a contradiction? Given that f dash of x is equal to 0. We are getting a contradiction. Why we are getting a contradiction? Because our assumption is wrong. What is our assumption? F is not a constant function is wrong. Therefore, f must be a constant function. Right? Which is a contradiction to our hypothesis, that is f dash of x is equal to 0, right? That's why our assumption is wrong. Therefore, f must be a constant function. Next, there are some definitions are there. Let f and g are differentiable functions on open interval a comma b such that f dash of x is equal to g dash of x on open interval a comma b. Then there exists a constant c such that f of x is equal to g of x plus c for all x belongs to a comma b. That means we can derive one function from another function by adding some constant, right? If f dash of x is equal to g dash of x, right? Now, strictly increasing. Let f be a real valued function defined on an interval I. We say that f is strictly increasing on I for x1, x2 belongs to I. If x1 less than or equal to x2, imply f of x1 is less than f of x2. Right? Simply, if the function values goes on increasing, then the function is said to be an increasing function. Just now, I have explained this example. No, see here. Now I am taking f of x is equal to x square for all x belongs to 2 comma 4. Right? Now choose two values. Say x1 is equal to 2.5 and x2 is equal to 3. Now what is f of x1 is equal to? F of 2.5 is equal to 2.5 whole square, which is 6.25. Now f of x2 is equal to f of 3 is equal to 3 whole square is equal to 9. Here x1 is less than x2, no? That is 2.5 is less than 3, no? Implies what you are getting? F of x1 is less than f of x2, no? What is f of x1 here? 6.25. Less than f of x2 is 9, right? for x1 less than x2, if f of x1 is less than f of x2, then the function is said to be strictly increasing function. Strictly increasing. That means if the function values goes on increasing continuously. Then what is strictly decreasing? Let f be a real valued function defined on an interval I. We say that f is strictly decreasing on I. Same definition. For x1 comma x2 belongs to I and x1 less than x2 implies f of x1 is greater than f of x2. Remember this one. For same condition, if f of x1 is less than f of x2, then it is increasing. If f of x1 is greater than f of x2, it is strictly decreasing. That means the function values goes on decreasing. You can take the same example for this one. F of x is equal to 1 by x for all x belongs to 2 comma 4. See if you want, x1 is equal to, I am taking 2.5 again, x2 is equal to 3. Here x1 is less than x2, no? Yes, 2.5 is less than 3. Now calculate f of x1 1 by 2.5. F of x2 1 by 3. Now compare this one, 1 by 2.5 is greater than 1 by 3, no? That is f of x1 is greater than f of x2, no? Right? Therefore, this function is a decreasing function. For x1 less than x2, we are getting f of x1 greater than f of x2. See, therefore, the function is said to be a decreasing function, strictly decreasing function. Right? Now, f is increasing on I. When do you say that simply increasing? If it is less than or equal to. If it is f is said to be a decreasing means if it is greater than or equal to. That is the difference. Okay. Now some examples are there. F of x is equal to e power x and f of x is equal to root x. Right. Whether it is strictly increasing or decreasing, we have to check. Right. Now, and some properties are there. Let f be a differentiable function on an interval a comma b. Then f is strictly increasing if f dash of x is greater than 0. Right? F is strictly decreasing if f dash of x less than 0. F is increasing if f dash of x greater than or equal to 0. F is decreasing if f dash of x less than or equal to 0. Right? See, very simple statement in one line answers only. What is f? F is a differentiable function on open interval a comma b. And f dash of x is greater than 0 is given for all x belongs to open interval a comma b. Consider x1 x2, right, where a less than or less than x1 less than x2 less than b. By mean value theorem, for some x belongs to this interval only, we have f of x2 minus f of x1 by x2 minus x1 is equal to f dash of x, no, which is obviously greater than 0. That means by cross multiplying, since x2 minus x1 is greater than 0, see here, x1 is less than x2 means x2 minus x1 is greater than or equal to 0, no? Right. Imply that what we are getting, f of x2 minus f of x1 is also greater than 0, or if you transpose this term to right hand side, what you will get, f of x2 is greater than f of x1. That means f is a strictly increasing function. We got this definition, no? As per our definition. For x1 less than x2, if f of x1 is less than f of x2, sorry, decreasing, no? Yeah, right, just see. Therefore, which also can be written as or f of x1 less than f of x2, right? Therefore, it is strictly increasing. The values goes on increasing. See here, x1 less than x2 implies f of x1 less than f of x2 should get. We got the same result, no? F of x2 greater than f of x1, or you can write f of x1 is less than f of x2. Similarly, third one, f is differentiable, right? On OB, f dash of x is greater than or equal to 0 for x1 x2 belongs to a comma b and x1 less than x2, right? We are taking the same interval, right? See here, since f dash of x is greater than 0 for all x belongs to a comma b, that implies f dash of c is also greater than 0 for some c belongs to open interval a comma b, right? Okay, we'll continue the second one and fourth one in the next video, right? Both are similar. Decreasing means f of dash of x less than 0. Here simply what we have to take, simply you have to put less than, that's it, given that f dash of x is less than 0. Now since x2 minus x greater than 0 implies f of x2 minus f of x1 is less than 0, you will get, since f dash x is less than 0, no, now you will get an extra other condition, f of x2 is less than f of x2 or f of x1 is greater than f of x2 you will get. Therefore you can write f is strictly decreasing function for the second one. Okay.